in the same ACM panels.
And that gives an almost continuous path for the fire to spread.
Thermal images from a police helicopter show that the burning crown ignites cladding on the other faces of the tower.
There's actually a waterfall of burning material cascading off the upper floors of the building, off the crown.
You've got these flaming globs of polyethylene falling down the side of the building, setting fires lower down, which can then travel up the face of the building again.
This explains how the tower ends up engulfed in flame. But this escalating disaster plays a
path for the fire to spread.
Thermal images from a police helicopter show that the burning crown ignites cladding on the other faces of the tower.
There's actually a waterfall of burning material cascading off the upper floors of the building, off the crown.
You've got these flaming globs of polyethylene falling down the side of the building, setting fires lower down, which can then travel up the face of the building again.
This explains how the tower ends up engulfed in flame. But this escalating disaster plays out over several hours. Why don't more people manage to escape? According to eyewitness statements, many remain in place because that's what they've been told to do.
So Grenfell Tower, like a lot of buildings of this type, has a stay-put policy. And what this means is that residents, in the case of some sort of emergency, are not advised to leave the building.
The reason residents are advised to shelter in place is because each flat in the building, each apartment in the building is a discrete concrete box that is kept separate from the others, specifically for the purpose of fire prevention.
The entire policy is built around the original design of the building in non-flammable concrete.
The problem is that by the time this fire starts, Grenfell is wrapped in this flammable cladding and it's nothing like concrete anymore.
When the cladding is fitted, the stay-put policy is not reviewed. By the time it is revoked at 2:47 a.m., so much of the building is ablaze that most people still in the tower are trapped. Just one obvious question remains. How does Grenfell end up clad in material that is intensely combustible?
If you look at the original planning document from 2012 for the cladding that was going to be added to Grenfell, it was not aluminum with a polyethylene core. It was meant to be zinc with a non-flammable core, and this was the design approved by the residents of the tower.
An updated planning application submitted in 2014 is the first evidence of a change to the cladding type.
And you can see from correspondence between Kensington and Chelsea Council and the contractors why this decision was made. The correspondence lists requested financial savings to decrease the overall cost of the refurbishment.
This includes £290,000 that would be saved by fitting aluminum cladding instead of zinc cladding. There is nothing in these papers to suggest that they are aware this will impact safety. But the consequence is that it does. Ultimately, that decision costs 72 people their lives.
So we know how this disaster unfolds. It all begins with an attempt to reduce costs by replacing one type of cladding for another.
On June the 14th, 2017, just a few minutes before 1 a.m., a call is made to the London Fire Brigade. The caller alerts them that the fridge freezer in his fourth floor flat is on fire.
The fire brigade arrives minutes later.
But the fire has started to expand rapidly. The UPVC windows of the apartment have fallen out, and the fire has now escaped its initial location.
The flames set light to the flammable cladding on the outside of the building.
Thanks to the arrangement of the panels, which creates this chimney effect, the fire races up this side of the building.
Once it reaches the roof, The fire moves sideways.
The flames spread laterally around, dripping burning polyethylene onto the rest of the building and starting new fires.
The obsolete stay put policy means many residents remain in their apartments. By the time the fire is under control, 72 people have lost their lives. Many more are seriously injured.
Immediately in the wake of the tragedy, both the bereaving families and people across the country demand an explanation. The ramifications for the Grenfell Tower fire are ongoing and don't look to be resolved anytime soon.
After the disaster, there was a scramble to identify other high-rise buildings with this kind of cladding. And it turned out there are around 500.
The work to replace this cladding is ongoing.
So far, more than 900 people, survivors, bereaved people from the tower disaster, have received £150 million in compensation from the civil courts.
Despite the scale of the disaster, so far there have been no criminal charges. The Grenfell tragedy took hours to play out. But disaster can also strike in seconds. Eschede, Germany. A sleepy town in the district of Celle.
It's June 1990, and a high-speed train is zooming around the gently curved section of track just outside the town. And this is a popular service. Families, business people, all trying to get their destination as fast as possible.
The high-speed train is the pride of the German railways. As it approaches Eschede, it is traveling at 125 miles an hour.
Still going flat out, the train comes off the tracks and smashes into a bridge.
People are killed. 88 more are seriously injured. It is the worst high-speed train crash in history. Now, combining all the available evidence with cutting-edge digital technology, we will recreate the disaster and piece together the deadly chain of events leading up to it. To answer the question, what causes this catastrophe? The disaster at Eschede begins as a completely routine train journey.
The train in question is ICE 88. It left Munich on the morning of the 3rd and was heading to Hamburg. The journey was 6 hours.
The ICE 884 has 12 coaches, including a passenger coach, a restaurant, service coach, and then a locomotive on each end.
No footage exists of the accident happening, but careful examination of the photographic evidence helps create a disaster timeline.
Immediately after the accident, the front of the train, the locomotive, and the first two carriages come to a stop a fair way down the track, and they're actually largely undamaged.
The concrete bridge the train hits has collapsed.
Carriage 4 clears the bridge, but slams into some nearby trees. Carriage 5 half makes it under the bridge, the other half is crushed. And carriage 6, the restaurant car, is completely compressed to just 6 inches.
This suggests that the accident begins between carriage 2 and carriage 4, and the evidence backs this up.
It's the third carriage that's really suffered here. The back of that is derailed and it's swung off to the right.
This points to the disaster beginning with the derailment of carriage 3. What causes that? A piece of vital evidence comes from the minutes before the crash.
We have various witness statements. There's one that is particularly important. This comes from Morgan Dickman, who was sitting in the front carriage. According to Mr. Dickman's statement, a huge piece of metal shoots up between his wife and son, so he runs off to tell the guard.
Dittman says that the attendant refuses to pull the emergency brake until he has personally verified the damage, because that is standard Deutsche Bahn policy. Unfortunately, just as they walk through that door, the train crashes.
Analysis of the piece of metal that Dittman sees reveals there is only one thing it can be: the outer rim of a train wheel. And photographic evidence shows damage to railway sleepers several miles back from the crash site, which must have been caused by the bottom of the broken rim protruding down through the carriage floor and hitting the track.
And that ties in with Dickman's witness statement, as he says that the carriage was swaying around quite violently, probably because of this piece of loose metal.
But if this rim causes the disaster, why doesn't the accident happen immediately rather than miles down the track? Very close to the collapsed bridge, there is evidence of an anomaly in the track. A section of guardrail is missing. Guardrail is used along the edges of the track to keep the wheels on the rails at junctions. At Eschede, it has been torn out.
This guardrail must have been ripped up by this protruding piece of metal from the rim of the wheel.
That fits with the evidence found in carriage 1.
They find the guardrail a few feet away from the wheel rim, and it's penetrating from floor to ceiling.
This is a much larger piece of metal than the thin wheel rim.
Imagine this huge rail smashing up through the bottom of the carriage. That'll be enough to lift that whole carriage up.
Video shows that the rear axle of carriage 1 is off the tracks. The obvious cause appears to be the impact with the guardrail. But carriage 1 is almost undamaged, and it's clear from the accident scene that the disaster begins with carriage 3. So what actually happens?
If you look at the track layout, there's a set of points and switches which divert the train off the main line to the branch line.
By the time the train reaches these points, all the evidence suggests that the rear wheels of carriage 1 have already derailed.
The switch rails can be knocked by something. So, for example, a pair of wheels that are no longer fully on the track. And if the switching were to happen, then the train would be diverted from the main line that is currently speeding along onto the branch line.
The evidence from the crash damage suggests the front of carriage 3 clears the points before they finish swapping to the branch line. But the rear is diverted, taking all the carriages behind with it.
So now we've got a situation where the front part of the train is shooting down the main line, and then those rear carriages have been directed onto the branch line. And all of this is happening at 125 miles an hour. That's enough force to rip the train into two, and explains why the locomotive was found basically intact.
It is now clear what causes the initial derailment, but most of the devastating damage is caused by the bridge collapse that follows. Why does the bridge fail? The high-speed train at Eschede is traveling at 125 miles per hour, but it derails just before reaching the road bridge.
If we're trying to work out why the bridge collapsed, we need to look at the pattern of damage on those carriages. Carriages 1 and 2 are looking largely intact. The right-hand side of carriage 3 is really badly damaged.
Carriage 3 must have hit something side on, and that fits with the evidence that the points are switched while the train passes over them.
The first two carriages make it under the bridge. The second half of carriage 3, the back wheels go down the branch line, twisting the whole carriage, moving it sideways, slamming it into the bridge.
The bridge is supported by concrete pillars at the trackside. In this accident, they are a fatal design weakness. The Damage to the derailing carriage 3 tells us that it must have hit these vulnerable pillars at very high speed. Without their support, the bridge collapses on the train as it passes underneath.
Any carriages coming in behind have nowhere to go, so they just plough into the carnage.
88 people were severely injured. 101 were killed. It all begins with the failure of a steel wheel.
We know how it's done. The big question is, how does the rim come off the wheel in the first place?
The maintenance history of these trains reveals that the wheels have been an issue in the past.
If you look at the very high-speed trains, their wheels are made out of monoblock, a solid piece of steel. The problem with the monoblocks is they cause lots of vibration, and this was particularly noticeable in the restaurant park, where the glasses would clink together.
So to provide a more comfortable ride for passengers, these monoblock wheels were replaced with what's called a duoblock wheel. And this is a wheel in 3 parts. There's a central hub, then a thin layer of rubber, about 20 millimeters thick, that's a bit less than an inch, that absorbs some of those shocks, and then a steel ring around the outside, which is called the tire. And this construction makes a much more smooth ride for those wheels on the train.
Dual-block wheels are fitted on the Echelon train.
We know that somehow that steel tire around one of those dual-block wheels comes completely off and shoots to the floor of carriage number 1. The question is, how and why?
The clues lie in understanding the mechanics of how the dual-block wheel behaves at high speed.
Because of the flexible nature of the rubber inner rim, you've got this constant distortion of 2 steel parts. That's what contributes to the vibration, because at high speeds, you're moving from a circular shape to an oval shape.
This constant flexing slowly weakens the rim through a process called metal fatigue.
If you wanted to break a paperclip, for example, you would just keep bending it, fatiguing it, making it weak. And that's exactly what happened to the outer wheel rim.
But fatigue cracks take time to form. Why aren't the warning signs spotted during routine maintenance?
One of the most shocking things were the witness statements by the Deutsche Bahn engineers. Rather than conducting vigorous safety checks on the wheels, they were just doing a visual inspection.
The obvious problem with the visual inspection is that crack needs to be big enough to see, and you're just never going to pick up these tiny hairline fractures that are typically found with medical team.
There is one final alarming piece of eyewitness evidence about the actual train that crashes.
In the weeks leading up to the crash, staff travelling on ICE 884 mentioned increased noise and vibration coming from a particular set of wheels.
This is almost certainly a warning sign that the wheel rim is failing.
Unfortunately, nothing was done about it.
The sad thing is that this whole disaster might have been averted if the train company had just been more diligent with the way it maintained its trains and their wheels.
There is now enough information to reconstruct the chain of events that leads to this tragedy. It begins 7 years earlier with the introduction of a new type of wheel.
A few minutes before 11 a.m., ICE 884 is travelling towards Hamburg at 125 miles per hour. The outer rim of the wheel snaps off and punches up through carriage 1.
The broken wheel rim rips up a guardrail. This lifts the rear axle of carriage 1 off the track, derailing it.
Seconds later, as that derailed wheel hits a switch rail, it switches the wheels and redirects the back part of the train onto the bridge.
The locomotive and the first 2 carriages make it under the bridge, but the third carriage twists sideways, slamming into the bridge, and the bridge collapses.
The rear part of the train smashes into the collapsed bridge and the massive carriages that have been crushed beneath it. This whole thing has just taken a few seconds, and yet 101 people are dead.
Following the disaster, there are major changes. The bridge is rebuilt with a cantilever design that doesn't have the vulnerable pillars. Duo-block wheels are immediately removed from every ICE train and replaced with the original monoblock design. Today, ICE trains remain in service, carrying millions of passengers every year. Buildings
There was no warning.
at sea,
Innocent people died.
in a train,
Everything was on fire. Everything was burning.
disasters can begin with the smallest things.
Changing the opening hours of a restaurant.
Three jobs. Paperwork.
Now, combining the latest research with every available source of evidence, experts will forensically analyze 3 disasters, down to each tiny detail.
We really built a thing outside.
You have to work your way back and understand each little change.
State-of-the-art graphics reveal every critical detail and every critical moment.
This whole disaster could have been averted.
We can dissect it, get inside, or underneath, freeze time, and even reverse it. To conduct a complete disaster autopsy. The town of Damascus, Arkansas. September 19th, 1980.
Fireball erupts out of the ledge, hundreds of feet into the air.
This is an enormous explosion which tosses chunks of concrete and steel the size of buses into the air.
The precise location of the blast sends a ripple of fear through the U.S. Air Force.
This site houses a Titan II missile, a 103-foot tall weapon of mass destruction.
Witness this launch of a Titan II.
The Titan II is a nuclear-tipped intercontinental ballistic missile. At Damascus, it is housed in a multi-million-dollar underground silo. Or at least it was.
The silo doors are gone, the area around is a ruin, and the missile is just not there anymore.
Now, combining declassified military records and key witness statements, we will digitally reconstruct the disaster to answer the vital question: how could a nuclear missile accidentally explode on American soil? The accident happens at Launch Complex 374-7.
The U.S. military builds their launch complexes completely underground in 3 main sections. You have the surface access portal at the top. Deep underground is the control center, deep enough to be protected from nuclear attack. And then you have the missile site itself, which is covered by an enormous steel door.
Filmed evidence after the explosion shows the scale of damage to this apparently impregnable structure.
The explosion is so powerful, it launches the 740-ton silo door into the air like a bottle cap. They find it 600 feet away from the silo.
The scale of devastation seems enormous, but compared with what the Titan II is built for, it's tiny.
The Titan II carries a 9 megaton warhead. That's 3 times the explosive power of all the bombs dropped by both sides in the Second World War, including the 2 atomic bombs on Hiroshima and Nagasaki.
But this cannot be a nuclear accident, as Arkansas is still here. So what does cause this huge explosion?
If we look at the missile in more detail, It is powered by two liquids. One is dinitrogen tetroxide, and the other is unsymmetrical dimethyl hydrogen.
Both are extremely dangerous.
They're incredibly toxic and nasty chemicals. And oh yeah, they're highly volatile and explosive.
Why would anyone use such unstable materials near a nuclear warhead?
When this site is built in the early 60s, the Soviet Union and the U.S. are locked at the height of Cold War paranoia.
These underground launch sites are hardened against nuclear attack.
Both sides have hundreds of nuclear-tipped missiles pointed at the other. What's keeping them from starting a war is a certain knowledge that any launch will be met with a devastating counter-launch. Mutually assured destruction.
This strategy relies completely on being able to launch missiles at a moment's notice.
You only have a few minutes from the moment you detect the other side's missiles in the air to get your own in the air before everything you have is wiped out. So speed of launch is a technological and strategic imperative.
Some rockets use cryogenic fuels, but these must be loaded immediately before launch, and that takes time.
The great advantage of hydrogen and nitrogen tetroxide is the fact that you can store them in the missile at room temperature, ready to go. And when you mix them, they form what is called a hypergolic mixture, which is perfect to power a rocket at very short notice.
Hypergolic fuels ignite instantly on contact with each other, but there is a price to pay for these advantages.
You got a missile full of these two fuels that, if mixed, will ignite, and you're storing it in the confined space of a silo. That's a recipe for disaster.
Do these volatile materials somehow come into contact?
The first accounts we have come from Senior Airman David Powell and Airman Jeffrey Plum. Their job was to transfer these highly volatile substances into the missile.
This is a high-risk occupation.
Both of these liquids are extremely hazardous. They're very toxic. In addition, dinitrogen tetroxide dissolves in your lungs to produce it.
To work with these extremely dangerous fuels, the workers have to wear rocket fuel handlers' clothing outfits, which are extremely bulky and have their own air supplies, almost like spacesuits. It is very difficult to do anything. They make the users very clumsy with their thick rubber gloves.
According to their statements, before the accident, the two airmen are working near the top of the 103-foot missile.
So one of the maintenance technicians picks up a ratchet with a socket on the end.
But Powell has the wrong type of wrench.
The socket falls out, bounces on the platform, and plunges down into the darkness of the main duct.
The socket falls something like 80 feet, bounces off the wall of the silo,
Up into the rocket, puncturing a hole, and highly volatile hydrogen gas begins leaking out.
If enough fuel leaks out, the pressure in the fuel tank will drop too far, and the missile will collapse under its own weight.
At this point, they're facing a ticking time bomb.
The launch site is evacuated and shut down.
The problem is that since everyone has left the silo, they have no idea how bad the situation is. So they ask for volunteers to go inside and take a reading of fuel concentrations in the air and try to stabilize the leak.
Airmen Rex Huckel and Greg Devlin volunteer to go in. Their statements provide the first evidence of what is happening in the silo.
They suit up to enter the missile silo complex. It's on lockdown, so they have to break in.
Records show that they entered the evacuated complex around 2 a.m.